Hi everyone, we're Lukas and Robin from ZeroSync, and thank you guys. And today we are going to talk about the projects that we are working on, which is in particular Chainsa Proof of Bitcoin. The second is ZK Coins, which is a second layer protocol, and the third thing is BitVM. And Lukas starts now.
Yeah, at ZeroSync, we have really focused on, or we've been really focused the past 6 months on zero-knowledge proofs and how to apply them to Bitcoin. And what we thought of was what we call Chainsa Proofs. So with every solution, you have to come up with some kind of problem, usually, for people to sell it to. So that's a problem we are going to focus on for the first part of the talk, and it's the problem of bootstrapping a new node for Bitcoin. So right now there are millions of Bitcoin users probably, and only around 50,000 full nodes. The chain is super big. It's 500 gigabytes, and it's growing every year. So running an entire full node keeps getting harder every year, right? You have to download all the data from the peer-to-peer network, and it's annoying. So the question is, can we compress that some way and reduce the amount of data and computation we have to do to bootstrap a node while still keeping the same security for Bitcoin? And that's where apparently zero-knowledge proofs are pretty useful for. And I'm just going to take a shortcut here without explaining zero-knowledge proofs in detail. The idea is we just take the Bitcoin consensus rules and the blockchain data, we feed that to a prover that can prove a statement cryptographically for a verifier to verify. And while it's hard to prove it, the verifier can do so very efficiently. And so we feed the 500 gigabytes of data into the prover does some magic called math, and we end up with a state proof. That's what we call it, at least. And it's the state after a certain block in the chain. So it could be like the state after the first 1,000 block headers, blocks, whatever. Could also be the state after the first 800,000 block headers. So you no longer have to download 800,000 blocks. You just download a proof and a state corresponding to it. And that allows us to compress 500 gigabytes of data down to a single megabyte or maybe 2 megabytes of uncompressed data that you have to download and verify with a zero-knowledge proof verifier. So why is that great in the sense of Bitcoin? Just do utrix-o, right, activate some soft fork. And that's the great thing about zero-knowledge proofs. No drama here, no drama on stage, no forks required, and you can opt in to use that right now, or you can also opt out. Don't use it if you don't like it. Proofs are very detached from everything else. Like a proof really stands for itself, and once you have a proof generated, everyone can verify it. There's no setup required, no further communication other than serving the proof. So those can be reshared, and you can, using something called recursive zero-knowledge proofs, build up on a proof, right? So if I have a proof of the first 1,000 block headers, it would be annoying if you wanted to create a proof and have to do the same work I did to achieve a proof for the 1,000 block headers initially. You can just take my proof and add a block to it. So this is like what our roadmap looked like for, or still looks like, for the chain state proof. So we were first thinking of a header chain proof, right? So if you think of Bitcoin, there's the header chain. That's the easiest thing in Bitcoin I can think of. And we just prove the proof of work, the hash chain, and difficulty adjustments, and that the header chain is correct. We also did something which we call chain augmentation. So we were just constructing a data structure on the data we are validating in the ZKP. So the ZKP you can think of as it just runs a node in it that verifies the headers or validates the headers. And while you do that, you can build up any data structure you want. So we just made a Merkle tree over all block hashes. So now we can very efficiently prove that a block is part of a proof. Then the next step would be an assume valid chain proof. that verifies, validates all consensus rules except for the script validation, right? So you have these transactions, they have to be in a Merkle tree, the Merkle root has to be in the block header, and so on. And it also has to manage the entire UTXO set. And we have code for that actually as well, and we use UTXO for that. And then eventually down the line, you just want to have a full chain proof that verifies all consensus rules and even the signatures, and potentially the script. So this is implemented right now. The assumed valid chain proof, as I said, is also implemented, but this proof actually exists. And let's talk a bit about how we generated it. I already mentioned recursive Starks or recursive zero-knowledge proofs, and the idea was that you could not just run a huge computation forever, because I'm not going to live forever. No Bitcoiners will live forever potentially, so it will be quite hard to eventually get that proof. And instead, we chunked up the header chain into batches. So every batch was about 1,300 headers, and so we had a lot of proofs for a lot of batches of the header chain. But it's annoying, right? You don't want to download 50 proofs or more just to verify the header chain. You want to download a single proof. So we can aggregate them together by just verifying 2 proofs in another proof. Yeah, just stick with me here. It works apparently. Quite mind-blowing, but it works. And this way we were able to generate a single proof for the entire header chain. For the proving process, we just ordered 14 machines. On Amazon, nothing too crazy, 6-core normal machines, probably a bit more memory than your everyday laptop, I must admit. But in the end, we just started it, went on a hiking trip for 8 days, right, as any sane developer would do. And at the end of the month, we had a $4K bill waiting for us, and also a chain state proof for the headers. And you can actually use that and verify that right now on your phone if you want. If you just scan the QR code or look up zerosync.org/demo, it takes about 5 seconds on an iPhone, and it is maybe 200 kilobytes of data you have to download. So really not that much, and already 50 times smaller than the header chain right now. So just imagine what could be possible if it contains the full chain. And we're talking about 500 gigabytes and not 64 megabytes. Okay, thank you. I think that was my part, and I'm going to leave you in the hands of Robin now.
Thank you, Lukas.
Thanks,
we started out with a chain state proof, but working on a chain state proof, we looked at other Bitcoin protocols that we could maybe enhance using ZKPs, zero-knowledge proofs, and we looked in particular at protocols like RGB and Taro, and we found out ZKPs make them vastly better. And we designed a protocol that is basically RGB combined with zero-knowledge proofs. And now I'm going to talk about its properties and why it's cool. First of all, it starts with a great idea that Andrew Poelstra said in, I think, 2017 in a talk about scriptless scripts back then. He said we should use the chain for what the chain is good for, which is to create an immutable ordering of commitments to prevent double spending. And that is a very, very powerful idea, and I think that's the way how we should design blockchains and how we can scale Bitcoin a lot more, or like the on-chain capabilities of Bitcoin. And there is an idea called client-side validation, which has already been proposed by Peter Todd in, I think, 2016. And it matches pretty perfectly the idea of Andrew Poelstra. And the idea behind client-side validation is, in general, if I send you a coin, then you, as the recipient, you are incentivized to verify the validity of that coin. Because you want me to send you real money, so you check that it's real money, right? And we can do most of that off-chain. Like I can send you the entire history of a coin off-chain, and then you can just verify the entire history, and if that history is correct, then the coin is probably correct. The only thing you cannot verify off-chain is double spending. You don't know if I spent that same valid coin to someone else. And that's why we need the chain for. That's what we need the chain for. And yeah, as I said before, RGB and Taro, they are protocols that already implement that. They are based on these ideas that I just said. And it's cool that no fork is required. It just works on Bitcoin as it is. However, it has fundamental limitations, and the first fundamental limitation is that the history, like that history proof that I have to give you, it grows quasi-exponentially because every transaction has at least one predecessor transaction, and on average it has more than one predecessor transaction, so you have that tree of previous transactions, and that becomes like potentially super huge. And if I had to send you like gigabytes of data at the supermarket cashier or something, that wouldn't make much sense. We want to have that more compact. And the other thing is we cannot easily have Bitcoin on ZK on client-side validation protocols because we would need some mechanism to peg BTC to that other protocol. And currently, there is not yet a solution for, but sorry? Yeah. Okay, ZK coins is the idea to combine RGB with with validity proofs to compress that entire token history to basically a negligible size. And this way, a coin becomes its proof of validity. It's not that I give you the history of the coin. I don't give you like a million transactions that are in the history of the coin. I just give you like a very succinct proof that this particular coin is correct, and you can verify it basically instantly. And yeah, then you know the coin is correct. And it has all kinds of cool properties. You can have up to 100 on-chain transactions per second. You get perfect privacy. You can obfuscate both the transaction values and the transaction graphs. And this gives you like Zcash level privacy, basically. You don't have to bloat the UTXO set. You can completely decouple ZK coin UTXOs from Bitcoin UTXOs. So you could have like 1 billion ZK coin outputs without increasing the UTXO set by any bit. And another cool thing is that you can pay the transaction fees directly in tokens. For example, if it's Tether, I send you Tether, and then you can send this Tether to the next person without having to acquire some BTC first. And it's cool for interoperability. If you would like to have like USDC from the Ethereum chain and peg it to Bitcoin to trade it trustlessly against Bitcoin, you could easily do it because these proofs are so nicely compact that you can easily transfer them from one chain to another. Yes, but there are also fundamental limitations. The first one is the proving. Like, can I just generate such a proof on my phone within seconds? That is not clear if that is just easy. And the second thing, of course, yeah, we cannot trustlessly bridge BTC to such a protocol. Big question, of course, when mainnet? We just started a research collaboration with Blockstream. We want to come up with a protocol specification soon and to share it with the community to get feedback and like iterate on it. I already mentioned the proof system is a big question. Which proof system is fast enough to do that? There are proof systems like Plonky 2, for example, that might be well suited for it. Another hot topic is currently folding schemes. They might be even more efficient. And it is quite likely that this is solvable. There are lots of very bright people in the cryptography research area, and they are solving this problem soon, I would bet. Yeah, and once we have that protocol specification and got like feedback and iterated on it, then we will build a first prototype and give people something to play around with. The only remaining question is, how can we have a trust minimized bridge, right? Because we want bitcoins, we don't want shitcoins. So that was like the only open question here. And yeah, that's why we came up with the BitVM, which has been a hot topic this week. First of all, I admit it is a bit overhyped. We have to talk first about what it cannot do. We cannot have just like an EVM on Bitcoin. We cannot instantly kill all shitcoins, unfortunately. We cannot solve all the problems. We will not have world peace immediately. And we unfortunately cannot emulate all soft forks automatically. But maybe it's just a research problem. Maybe at some point we can have finally our EVM on Bitcoin and like kill our shitcoins instantly. Not sure yet, but maybe. But I'm not claiming that it's possible. Now the interesting part, what it can do. First of all, we can have a virtual machine in the proof of verifier setting. That is the main differentiation. Usually in smart contracting systems, they are trustless, permissionless. Everybody can interact with every contract usually. And that is a fundamental difference to the BitVM. In the BitVM, there is a prover and a verifier, and they have to make that dance up front and then commit in the chain, and then it's exactly that prover and that verifier. And other people cannot easily interact with that. That is a fundamental limitation of it. But however, once we have set that up, we can run arbitrarily complex computation on Bitcoin. And that is a big thing. That is really new and will change a lot, I think. And of course, it doesn't require a soft fork. That was like the main design goal. And in the happy case, as long as both parties agree, they can settle everything off-chain. What hits the chain is indistinguishable from like a regular taproot transaction. And that is quite a powerful feature. Only in case if there is a dispute, then they have to do like an on-chain dance to figure out who actually lied. And I think that will enable a huge design space for novel applications, and it will be very interesting to exploit. Maybe it can even bring Jeremy back. I don't want to promise too much, but it might be possible somehow. Don't want to promise too much here. How does the fundamental mechanism work? Well, the first fundamental idea of it is to have a way to have state across different scripts. Usually Bitcoin is completely stateless. Every script is executed by itself, and all other scripts have like nothing to do with that execution. And we came up with an idea called bit commitments, and that is essentially a way to have state across different scripts. And that enables something way more powerful than script without it, than stateless script. Everything is expressed simply in binary circuits. Like the most complex computation can be broken down to binary circuits. In general, you can break everything down to a NAND gate, but you just need these circuits to express computation. And then you represent them in huge taproots, in huge tap trees. And the fundamental idea here is don't execute verify. Many people got that wrong. They thought we would execute everything on the chain, but the cool thing here is you only ever have to execute anything if you disagree with each other. One party makes a claim and the other party is like, no, that's not true. So to disprove them, they just have to find like one particular path in the program that was executed incorrectly. And only that particular path has to get executed on chain to prove that this person actually lied. All of the rest of the computation, there could be like billions and billions of other cycles that were all executed correctly. They don't matter. They will never touch the chain. We have to touch the chain only with that one state transition that was executed incorrectly. Or with the first. There could be many that were executed incorrectly, but the first one that was executed incorrectly, that is what we drag onto the chain and resolve it on chain. And there's like a challenge response protocol where prover and verifier basically do a dance where like challenger says, hey, this is wrong. The prover says, well, here is my response to that. And then the challenger says again, well, if that is true, then what is about that? And then it asks clever questions until the prover contradicts itself. And once the prover contradicted itself, you can slash them. The most awesome feature that is enabled by this so far is trust-minimized bridges. That's really what we want. We want to bridge Bitcoin to more expressive protocols or to more feature-rich protocols, for example, ZK coins, such that we get better scalability or perfect privacy and all these neat features. And we can minimize bridges by having one prover, but many verifiers. Like there's one prover and there could be 100 verifiers. And as long as a single verifier is honest, then we get both safety and liveness. So everybody, like nobody will lose their money and nobody's money will get stuck. And that requires only a single honest verifier. And we could probably cascade that even, that we have verifiers who verify the verifiers. And that increases the number of participants, because if we have the assumption that 1 of 100 is honest, that's a much stronger assumption than 1 in a million is honest. And if we could have 1 million people, if we could cascade it such that there are 1 million verifiers in the end, then it could be pretty much trustless. And in particular, if you can participate yourself, if you can be a verifier yourself, then you can know that is for you trustless. Like for you subjectively, you can always slash a prover who is lying if you are one of the verifiers. Yeah, and if we just allow enough verifiers, then or like if we can enable enough verifiers, if the protocol can support enough verifiers, because there's a problem, we cannot just have like 1 million verifiers in the first stage. That doesn't work out in practice. But yeah, the more verifiers we have, the more trust minimized that bridge is. That's basically the takeaway that we should have here. Yeah, and another misconception was that people thought we would express like all the computation in quirky binary circuits, but that's not true. The idea behind it is to have a virtual machine, and then we have circuits that can disprove a single state transition of that, or like a single faulty state transition of that virtual machine. And that is extremely powerful, because we can basically have, like for any practical purposes, unlimited memory, and for any practical purposes, unlimited cycles. We could run that virtual machine basically forever, as long as we want, mostly. And yeah, we will just implement a basic instruction set, and then you can even compile high-level languages down to it. You could use like your favorite Blake 2 implementation and just compile it down to this virtual machine, and then you can you can verify basically any crypto function on Bitcoin, or you can take existing code and just compile it down there. And the idea behind that is that building these circuits is very error prone. Like it's very hard to like figure out every bit. That's usually not how you program. You program from high-level languages, and then you compile it down to something more simple, so more closer to the machine. Next question, of course, when mainnet? We're gonna have a hacker house this October, hopefully, and then we're gonna lock ourselves into a house for 1 week and hack our brains out until we have an initial version of this VM. And then we can give people something to play around with and to like look at the code and see how it all works together and like answer all the questions, and in particular explore the possibilities of the VM, like what is possible with it, what is not possible, what can we do with it. Takeaways. First of all, zero-knowledge proofs enable groundbreaking compression. We can really compress the chain from hundreds of gigabytes down to megabytes. In general, proof systems are likely the future of Bitcoin. They're extremely powerful, and we will probably see them being applied in many areas of Bitcoin. There are lots of other applications beyond what I mentioned here. And the ZK Coins protocol gives you scalability and privacy, and the BitVM enables arbitrary computation, and in particular, trust-minimized bridges. It was only 2 weeks. And that's it. Yeah? Okay. I just heard we got some time for questions. I think you were the first.
Hi, Robin.
Hey.
Can you hear me? Yeah. I'm also Robin. From
cool name.
So we're building an ordinal lending platform. We're using DLCs for this right now. So
you're using what?
An ordinal lending platform. So you can use an ordinal as collateral and borrow Bitcoin against it. Mm-hmm. And we're using a DLC to escrow the ordinal at the moment. And then there's an oracle attached to it, which kind of checks if the borrower repaid the loan or not. But obviously, like, an oracle is not perfect. And I wanted to ask, like, how could an implementation work with ZK rollups or with the BitVM, like, to escrow something like an ordinal, because it's technically Bitcoin? It's a tough question.
Yeah, I mean, you could use a similar mechanism as we are using it for the bridge. You can basically prove any kind of statement of things that are in the blockchain. And if you have like some trusted or trust minimized party that is facilitating these things, or like is signing transactions, then you can slash them if they sign something that doesn't follow your protocol.
So it's possible to like basically let everything like read the Bitcoin blockchain to see what happened on the Bitcoin blockchain and create executions based on that.
Yeah.
That sounds really promising.
Yeah. Yes, please.
Yeah. So my understanding is in BitVM, you said you can have many verifiers and then you have one prover, right? And so it's kind of like a one-to-many or a one-to-one. If you're doing a peg out, how would you peg out the Bitcoin to someone who's not a part of, to a different person, essentially? So I peg in Bitcoin to a sidechain, I send it to Robin, he sends it to you, Robin. Then how do you peg it back out yourself as someone who's maybe not in that same BitVM construct?
Yeah, like the prover here would be the bridge. Would be the federation that facilitates these things, just like in Liquid. The only difference here is that the prover puts up a deposit, and when he does anything that doesn't follow the protocol, like giving money to someone who did not follow the protocol, then you can slash them.
Thank you for the presentation. I was going to ask, like, after the setup of the BitVM, can't you just leak the private key of verifier so that anyone can challenge the prover?
That's a good question. I thought about that too. However, there is that problem that the verifier could ask dumb questions. Like he could ask questions that don't really reveal anything about the incorrect execution. And you have to end the challenge somehow. Like it has to be a maximum number of challenges that the verifier can do. Because if the verifier challenges for no reason, then it has to end at some point. And a malicious verifier could just waste all the queries, and then you cannot disprove.
Awesome. Okay. Hello. Yeah. Awesome stuff. Congrats. The beauty is, of course, that it's very easy to verify the proof very quickly, but the proving is very difficult. So you have just one prover. How do you deal with one prover in an adversarial environment and making sure the protocol remains truly censorship resistant?
It feels a bit like we confused you a bit by mixing up terms. There's like the zero knowledge proof thing, and you have a prover and verifier there. And because we were so familiar with these terms, we just applied them to the BitVM as well. And in the BitVM, things are a bit different. It's like not that hard to set up this circuit, I think. Like there is not that fundamental asymmetry between prover and verifier in the setup. But the other question was like, you only have one prover, and how can you ensure that this prover follows the protocol? Well, it's just that you have a number of verifiers, and each verifier can verify that the prover actually follows the protocol. And if he defects, then you can slash them. Yeah, I mean, it's always about the prover puts up some deposit, and if he does something that defects, then you can take that deposit. And then the question is, what do you do with the deposit? You could like have a multi-sig of all verifiers, or like depending on the protocol, you could burn it. You could, it's these. Yeah. These ideas are kind of like, kind of obvious when you think about it, but the problem is that you quickly run into like combinatorial explosions, right? That what if this prover defects, and then you slash them and give it to the next prover, and he defects also. But yeah, we are thinking along these lines, and we are trying to minimize trust even more. And it's definitely an open research question. What are the limitations here? Like, how far can we get? One more question? You already have one. We can talk later.
You mentioned, you mentioned bit commitments as a mechanism to carry state.
Yes.
Because you can run any arbitrary amount of computation. So how would that work and also off-chain and on-chain verifiability of carrying and sharing some state bit commitments?
Yes. Okay. How not to blow up the scope of this here? Essentially, it's like 2 hashes, and you reveal one of them to set the value of the bit. And you have hash 0 and hash 1, and you reveal one of these hashes. For example, you reveal hash 1, and that's how you set the variable of this. You set the value of this variable to 1 by revealing this hash. And the commitment is not like a hash commitment, which is computationally binding. This is just like incentive binding, because if you ever reveal the other pre-image, then I can slash you. There's another path in the taproot tree, such that if I know both your pre-images, then I can take your money. And this incentivizes you to reveal exactly 1, like at most 1. Am I making sense? Or? You have 2 hashes, and you reveal one of these pre-images. Yeah? And if you reveal both pre-images, then I can slash you. And this is how you set the value of this variable. I see I'm not making sense, but I can try to explain it again off stage here. Okay. I guess that's it then. Thanks a lot.
Thanks, guys.
Thank you, Miami, for the last 3 years in this amazing city. The whole world shut down, but Miami welcomed us with open arms. We want to show Bitcoin to the whole world. We are taking the conference on the road to set the stage for Bitcoin in a new city. Nashville. Bitcoin 2024 is coming to Nashville in Tennessee, a city that is known as a music and freedom city. Bitcoin 2024 in Nashville from July 25th to 27th.